So next, we are okay in this class. We are going to discuss about binary search tree concept. The previous class we have discussed about tree traversal concept. Now we are going to discuss about the binary search tree. You all know about binary tree means. Binary means two. Every node has at most two children. The same binary tree property. Additionally, we are going to discuss about search tree concept. So what is binary search tree? In this binary search tree means every node here, the binary search tree is a tree, okay, is a binary tree in which every node contains only a smaller values in its left subtree and only larger values in its right subtree. Every node, okay, and this binary search tree is also called as a ordered binary tree. So ordered binary tree is called as binary search tree. In short, we can say it is a BST. So the properties of binary search tree is it should be a binary tree and the root node. Take a root node key value. Lesser than this root node values are placed as a left child and greater than this value of root node is placed as a right child. Okay, so this is called as the property of left subtree, that is binary search tree. Okay, and this is a simple example. Okay, let us take a 25. Okay, so next 25 means is a root node. So lesser than the 25 means 0 to 24. So the 0 to 24 we can place as a left child and greater than the 25 like a 26 to any number 100 thousands. So we can place as a right child. So, but here the logic is in every subtree also we have to check the same property. Root node may have some key lesser than the root node left, greater than the root node right. Okay, likewise here the 10. Lesser than the 10 is 5. Lesser than the greater than the 10 is 12. It's a right of 10. Likewise, lesser than the 5 is 1. It is placed as a left child. Greater than the 5 is 8. So that is placed as a right child. Even though this 10 is a main root means this whole will be lesser than the 10. Likewise, here the right of 10 means the whole will be lesser greater than the 10. Likewise, in this whole value, how many values we have placed, all should be lesser than the 25. And then all, this right hand side, all should be greater than the 25. So this is the property of binary search tree. So every node, okay, for say, for example, the root node has a key value, the key. Okay, here the value is called as a key. The each circle contains some value, so that is called as a key. So here the key is present. So lesser than the key is placed as the left hand side child and greater than the key is placed as a right hand side child. So here every subtree also we have to maintain the same property. Root node value is okay, root node is have a key. Lesser than the value are placed as a left child, greater than the value are placed as a right child. So this is the property of binary search tree. So next we will discuss, yeah. Also check whether, okay, these here the three examples are given. Just check whether this is a binary search tree or not. So here this is the first. Let us take this example. Here 21. Yes, it is a key. Okay, lesser than the 21 is placed as a left child. Here the rules violation. And here greater than 28, 27, and here this part is correct. Here 28, lesser than the 28 is 27, yes, correct. And greater than the 28, 39, correct. So this whole three, this all three values are greater than the 21. This is also correct. But here the violation at the left hand side. So this is not a binary search tree. And let us take this example here 21. Oh, lesser value is 20 is placed as a right child, left child, and here the greater value is placed as a right child 28 and 27, 39. Now this is called as a binary search tree, no violation. But check with this tree. Yeah, 21, 19 is lesser, yes, correct. But 17 is lesser, correct. But here 42 is greater than the 19, but it is greater than the 21. It is violate the property. So this is not also is here the 28 lesser value is placed as a left child. But here the whole value is greater than the 21. This 15 and 18 should be lesser than the 21. So this is also rules violation. So these for left child and sorry left hand side example and this example both are is not a binary search tree. Only this middle is called as a binary search tree. It will satisfy the property correctly. So the root have a key, lesser than the key is placed as a left child and greater than the key is placed as a right child. So this is called as binary search tree. This is a very, very important topic. So what is the use of this binary search tree means? for the searching in the database management system or any data storage. We need to access the data means we can easily access the data because the searching it will take half of the time, not the entire time. For example, in linked list means it's a linear manner. The elements are arranged to access the elements. It takes the number of elements. N elements means n accessing time. Okay, but in this B tree concept, it's a divide and conquer concept. So the search will be divided, not the search will be happen with the entire elements. For example, thousands of elements in the B tree means definitely our key value where our searched element will be either in one half. Okay, for example, we have a root of 500 is a root means lesser than the 500 is left hand side, greater than the 500 is called as the right hand side. So I need to search a value 300 means I have to compare with my root node value 500. So this 300 is lesser than the 500. So definitely I can go with the left hand side of child. Okay, so this searching will be reduced halfly. So within this left hand side child, again further we have a classification of less as well as a greater value in the root node. Likewise, we can divide the searching time half and half. So we can easily search the element. That is the advantage of binary search tree. Okay, next we will go with the operations of binary search tree. Okay, so here the operations are search operation, insert operation, and deletion. So search, okay, we have discussed already. The search means to search a element. Already we have, for example, in this example, we have some okay, seven elements are there. Out of this seven, I need to search five. So 5 means I no need to check with the entire tree. Just I have to take my searched value, the 5. So just I have to compare with my root node. 4 is equal to 5 or lesser than the 5 or greater than the 5. If sorry greater than the 4. So 5 is a greater than the 4. I can easily go with this right hand side child. A right hand side subtree. Again this right hand side subtree also again subtree structure. Compare with the root node. 6 is the lesser than the 5, so I can go with the left hand side. Now compare with this value 5, my input value also 5, both are equal, so the result is okay, success. The element was found. So this is called a search operation. So always the search takes the, okay, in BST it's a balanced tree. So search takes only the order of log n time, insertion also takes order of log n time, deletion also takes the order of log n time. Worst case time, search operation takes the order of n, as well as insertion as well as deletion also takes order of n time. So the worst case of binary search tree means the left skewed and right skewed concept. For example, 39 is a key. Lesser than the 39, all my value should be lesser than the 39 means definitely all will be placed as a left child. So this is the tree will be growed only in the left hand side. Here the right is biased. So this is called as left skewed. Likewise, in this example, 45, I am taking all values should be greater than the 45. So here the tree will be growing only in the right hand side direction. So here it is a left biased. So this is called as a right skewed. So in this left skewed and right skewed concept, definitely the worst case time complexity only we will get. In the average case, we will guess the order of log n time, but in worst case, we will take the order of n time complexity. So these are the time complexity about the binary search tree. So next we will take, okay, now we are going to construct the, yeah. So now we are going to construct the binary search tree for the given input. Okay, so here some element is given. So create a binary search tree using the following data element. So first step one, you have to take a step one. I am taking the first value 45, and now the my tree is empty. This is a newly inserted value. This is the first value of my tree. So this is a root. So 45 is inserted in the step one. So next I have to take it 39 is the second element. So while inserting this 39, I have to compare with this root node 45. Either this is the lesser than the 45 or greater than the 45. Yes, this 39 is lesser than the 45, so I can place this as a left child of 45. So second step. Okay, so now okay. So every time we have to satisfy the property of binary search tree. So here next element inserted is 56. So take a 56. Every time you have to compare with the root node. So to compare with the 45 first. Yes, this 56 is greater than the 45. Go to the right hand side and placed as a right child. And next we have to take a 12. So 12 means compare with the main root. Yes, it is lesser. Go to the left hand side. Compare with the next subroot and compare with this. Yes, it is lesser. So go to the left side. Place as a left child. Likewise, take a 34. Compare with the main root. It is lesser. So go with this 39. Again, it is lesser. Go with the 12. And again, compare with the 12. It is greater. So it is placed as a right child. Okay. Likewise, next 78. Compare with the main root. Yes, it is greater. And next compare with the next subroot. 56a is it greater. Go place as a right child of this 56. And next take it 32. Compare with the main root. The 32 is lesser. Go to the left subtree and compare with the next root. Yes, it is lesser. Go to the next root. And here is again 32 is greater. Go to the right hand side. Here compare with this root. Again it is lesser than the root. So place as a left child. 32. And next take a 10. So 10 is lesser than the 45, lesser than the 39. 12. Likewise, you have to keep on compare with every root. Either it is lesser than the root and greater than the root. Lesser than the root means place as a left child. Greater than the root means place as a right child. Here this 10 is the lesser than the 12. So place as a left child. So next take a 89. So it is greater than the 45. Move to the left hand side child, left subtree and compare with the 56. Yes, greater. Next move to the next 78. Yes, it is greater than the 78 and place as a right child of the 78, 89. Next we will discuss with the next diagram. Yes. Yeah, 89. So it is placed as a right child. And next take a 54. Again compare with the 45 greater and 54 is lesser than the 56. Place as a left child of 56. Next 67 means take a 67 compare with the 45 greater and 56 or a greater, and then next compare with the 78. Yes, it is greater and it is a left of the lesser than the 78. So place as a left child of the 78. And then take the 81. So 81 means greater than the 45, greater than the 56, greater than the 78, and then lesser than the 89. So place as a left child of 89. So this is called as insert operation. For every insertion, compare with the main root value and as well as subroot value whether the value is lesser than the key or greater than the key. Lesser than the key means place as a left child. Greater than the key means place as a right child. So this is called as insertion of binary search tree. And next is the algorithm. So whatever we have discussed, the same as algorithm. So we have to take a, okay, here this is search algorithm. So search the element, okay, in the tree with the value. If the compare the value, if the tree data equal to value or tree equal to null means return the tree, whatever the value present in the tree. Otherwise, if the value is lesser than the tree data, return the search element with the tree left comma value. If the else, if the value is okay, return the search element of tree right comma value. So first you have to take a search element equal to tree data means print it. Otherwise, it is lesser than the tree data means go to the left subtree and again search the element. Recursively, you can call the search operation. If the value is greater than the tree data, go to the right subtree and again call the search operation. So this is called as search algorithm. And next is, okay, here, and this is the again the search example. Take the 12, compare with the main root. Yes, it is lesser. Go to the next, it is lesser, and this is a right match. Okay, the input is also 12 and here is also 12. Both are available. So this is called as search operation. Okay, so and again this is search of 52 also same as 12. Okay, and inserting a node condition. So is this also already we have discussed same as algorithm. Take a insert value in the tree, and then if the tree is null means first we have to allocate the memory in the tree, and then the value is the first inserted value is the first node means set the tree data as a this new value. Okay, tree data equal to value. And for this node is the first node of the tree means there is a left and right for this node. So both are null. Else, if the tree contains already some existing value means you have to compare that value with the tree data. It is lesser means go insertion happen in the tree left hand side. If it is else means insertion happen at the tree right hand side with the value. So this is called as insert operation. So in this next class, we will discuss with the delete operation of binary search tree. Thank you.